So, all right, thank you. Thank you for joining us. The break's over now. And if you stepped out, welcome back. Uh, so the instructions, I think we're done with them for now. Unfortunately, we don't have time to keep troubleshooting. I'm sorry that we've had so many technical difficulties today. Uh, but we'll have to move on. This will be available later. We're going to make the slides and the tutorial available later. As well, if you have it on your machine already, it will work at any time. I mean, you can always run, where is it, Docker pull, because it's on Docker Hub now. It's online, so the only reason we've had so many troubles is internet. Well, that's not the only reason. All right, so one moment. Right, so we've got some info about recommender systems and game in particular. Yeah, now we have some context. We're going to move on to the more hands-on part, the more interactive part, the part with more practical aspects. So what might the data that we're going to be using game on look like? What might the configurations for a game look like? And the results, what might the results look like? And why do we want those results? So a quick overview, we're going to for those of us in the tutorial, fortunate enough, and for myself, please follow along. I'm going to switch to it in a second. What we're going to do is I'm going to give you some quick preliminary info about the environment. Then we're going to train some models using game, and it's going to culminate in a recommender system, a light one, that looks something like this. So you've seen this before, a little bit of previews with Bichang Shaoxing. What we've got here is we've got a little movie ratings app. And these movies come from the Movie Lens dataset. So right now they're being scored by the mean. Got the score here. That's the mean rating on the Movie Lens website. And what I've done is, playing a little bit of a character here, playing your grandfather, I've gone through and I've liked some films. Or I've rated some films to say. So I've gone and the character I'm playing here, they love Alfred Hitchcock films, but they do not enjoy sci-fi. So what I've gone through is I've given a 5 here to Rear Window. I've rated North by Northwest a 5. I've gone down. Star Wars, never heard of it. Ignoring it for now. What is it? Who knows? Kids these days. Vertigo, another 5. But Blade Runner, one time I saw this film Blade Runner, hated it. So 1 for Blade Runner. Now if we go up, and if we look at this model here, this is recommendations using just a standard fixed effect model. This is just what you get. Kind of, if you remember the Alice and Annie example, this is what Alice and Annie would have got without taking into account their features. So if you notice, it looks pretty similar. I mean, Schindler's List and The Usual Suspects swap places, Casablanca and Rear Window swap places. Nothing major here. But now let's take a look at what we can do by adding just a per user model, a random effect model. That's pretty different. So let's remove the ones I've rated here. And right off the bat, first one, Rebecca. That's Alfred Hitchcock film. Number 3, To Catch a Thief, Alfred Hitchcock film. 4, Spellbound, Alfred Hitchcock film. Now, Charade is not an Alfred Hitchcock film, but caveat, it's been described by some as the best Alfred Hitchcock film not made by Hitchcock. And the male lead is Cary Grant, who's also the male lead of North by Northwest, so definitely captured that info in it. Also, you can see that these films are older, so it's also catching some of the older films from the global model that were highly rated are here now as well. Casablanca, Laura, Maltese Falcon, It's a Wonderful Life, Citizen Kane. So, but you can still see some little peek through of the global model coming in. For example, The Usual Suspects isn't exactly like what I was rating I liked, but other people, it's similar enough, and other people love it so much that it's still peeking through. Now, if we go down, what do we got here? We got more Alfred Hitchcock films. Here's Shawshank Redemption. But we didn't just say, or at least I didn't just say that I like Hitchcock films. I also said that I don't like sci-fi. So if you recall, if we go back, Star Wars was number 10. And in fact, in the fixed effect only model, it was actually number 8. Wouldn't have been a great recommendation for this character here. But here, we got our first, let's check the first 100. So let's do a search for Star Wars. Nothing. Well, just in case, let's just do star and go through. Let's see what we got. No, 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 no. Nothing. It's gone. It's been bumped. So there we go. It's a little taste there to whet your appetite for what we're going to do today. All right. So let me just go here. Let me reset that. All right, one more thing before we move on. I'm sure you've already met them because we've had a lot of questions, but we're going to have a few assistants today, or these have already been your assistants. So we had Paul, Josh, Bichung, and Shanxing. They're kind of like our TAs. If during the more interactive parts of this, you still find you're having trouble, this time at least trouble, playing around, they'll be glad to help you. They'll be the first point of contact for all your questions. So if you've got a system question that didn't get answered before, please feel free to raise your hand and ask them. If you've got a technical question, they'll help you with that too. If for whatever reason there's an emergency, well, there's an urgent emergency, don't worry about them. Just shout, wave your arms. I'll help. All right. And the last thing is, again, I'm sorry that not everyone was able to set up the tutorial for themselves. Hopefully, if we make it available later, you can play around with it then. But please follow along. This will still be fun for everyone. All right, so is everybody interested? Is that something we'd like to do? Yes? A little interested. Okay, that's good. All right, so I'm gonna have to skip a section because we kind of everyone who would have been set up by now. So let's move on to the tutorial. So what we're going to be doing here is we're going to be running game from a Jupyter notebook that's running in a Docker container. So for those not familiar with Jupyter, it's fully configurable. You can double click here and play with the text. I'm not going to, but you can later if you're playing on your own, or you can do it on your own version right now. Basically, the most important part of this is that means the code. The code here is customizable, so you can play around with it. You can add your own stuff and run whatever you'd like. Don't run too much weird stuff. We want to keep with the tutorial. So up here, there's a little bit of an index. Here are the exercises we're going to go through today. One quick thing is, so down here, you see this click here for API documentation and glossary of terms. All three of those links go to the same place. That's how important it is, right here. So if you open this in a new tab, which I highly recommend, what you get is a glossary of some of the terms: fixed effect, random effect, mixed effect. There's a missing line. It's weird. Shard, feature set, and some visual examples. This is a glossary of terms in case at any point you forget what we're talking about, you want to look something up. Also, we're going to be dealing with game's interface, or at least a modified version of the LinkedIn interface to game. So in case you want to, these are new parameters. You're not used to them. So there's documentation here. Anything you want to look up, it'll be right here. Recommend keeping this tab open and coming back to it if you get lost or confused. And the best thing is at the bottom, there is a well-formed example of a configuration for game that uses all of the parameters that are up here in the documentation. So like I said, keep it open in one tab. Just keep an eye on it. Now, right here, everyone has a tutorial open. This is urgent. Please look at me. Now look at the screens. Right here, click on this on your screen and hit run. If you do not run these import statements, nothing will work. You'll get weird errors. So prevention is better than the cure. What was that? An ounce of prevention is worth a pound of cure. That's it, I believe. So there you go. Please run this right now. All right, so the game framework is part of the Photon ML library, which runs on Apache Spark, which is written in Scala. So what I'm trying to say is all this code in here is going to be Scala. Now, show of hands, who here does not like Scala? I see one over there, a couple more. You're a trendsetter, you let them say it. Don't worry, I'm not going to hold it against you. So we got some good news. We're pretty much not going to be using Scala very much. We're mostly going to be setting up some configurations. It's going to look more like this. It's more of a map. So don't worry about it. That's the good news for you. Now show of hands, who here does like Scala? Oh, more people. All right, well, I've got some bad news for you guys. We're not really going to be using Scala. We're mostly going to be setting up configurations. It's going to look more like this. All right, so just to do a quick run, for those unfamiliar, what this is going to do is it's going to take this list of integers stored as strings. It's going to convert them to actual integers. So if we run it, we can see, boom, there you go. Now, just to prove that we do, in fact, have all of Apache Spark in here, we can do it the Spark way. You can parallelize that list and then do the same thing. And just in case we have any more skeptics out there, you can actually explicitly do this. So if I do org Apache Spark RDD, and then go over here, This should still run. There you go. See? Not line. By the way, when you're on a cell, the way you want to run it is you want to hit Shift and Enter at the same time. That's what runs it. And you can also hit this Run Cell button up here next to the square that means stop. You can do the Run Cell button here. So one last thing before we move on. You might find it important or useful to run some shell commands while you're in here. Now, these code blocks are set up for running Scala, not shell. But luckily, Scala allows us to run shell code. So what you do is you wrap it in quotations, make it a string, and then you have the bang. So command bang. In this case, let's take a look what's in our data folder. There we go. You guys should only have heart, movie lens, and search ads. I've got a bit more because I fast forwarded in the tutorial to do those ratings. But there we go. One more thing is I'm going to leave a question section, quick questions, open between the various sections of this tutorial. So this one will be our first one. Are there any questions right now? None? Okay, so let's keep going then. So what we're going to do is we're going to incrementally build up to that system I showed you in the beginning with the ratings app. So the first thing is just kind of like a warm-up. We're going to train a fixed effect model only. Just the standard generalized linear model problem. It's going to be logistic regression. Nothing too difficult. So let's take a look at our data that we're going to use for this. Before we move on to the movie lens data set, we're going to have this heart disease data set here. It comes from UC Irvine. Any UC Irvine? Got a request to make the font larger. How about that? Is that better? Thumbs up at the back, please. Thumbs up or thumbs down? All right. I got 2 thumbs up and 2 thumbs down. Is that better? Now I'm getting 1 thumbs up, so voting doesn't work. All right. So yeah, it comes from UC Irvine. Is there any UC Irvine alumni here? Yeah, there you go. I'm not from UC Irvine. I'm just enthusiastic that you are. So let's take a look at what this data looks like. So here we go. This is what our Avro record containing the data is going to look like. We've got our response. That's our label. That's 1 for heart disease, 0 for no heart disease. The offset, it's like a partial score that's added to it during training. We'll make use of that later. Weight, that's the weight of the record relative to other records. And here we go. Features. This is our, where is it? That's down here. This is our xij here. So this is the feature vector that we're going to be learning. Whoops. Right here. So you can see we got age, sex, CP, I'm not quite sure. This one's cholesterol. They've all got names. If you go up the link here to find more info about the heart disease data set, you'll see what each of those is exactly. So that's what we're working with. And now let's take a look at what our game configuration might look like for that. So a quick run through of these parameters. We've got input paths, that's the paths to our training data. Validation paths, paths to our validation data. Output path, that's where the output from game is going to go. These feature sets paths, shard to feature sets map, and update sequence. Let's skip those for a moment. Task, in this case, logistic regression. That's what we're doing. If we were using a different data set, that could be linear regression, Poisson regression. Num iterations I'm also going to skip for now. We'll come back to it in the next one. It's not important till then. So the fixed effect data configs, this one is an important one. This is actually how we're defining our fixed effect problem. So what we're doing here is all the fixed effect problems have their definition in this guy. So we're creating a fixed effect problem named global. This is what we're going to be solving. And we've got this, for those familiar with Spark, we've got the num partitions. That's the minimum number of partitions for the RDD. It's going to be made out of the data. It's not too important. The important one here is this shard ID as global shard. So now, what exactly is a shard? For those unfamiliar, shard comes from database nomenclature, terminology. And just like you can, so let's say we have our data. We have this record here, and we have a bunch of these records. We could picture it as a data table, like an SQL table. So every row would be a record, and every column would be a feature. So in addition that we've partitioned vertically by records, each row is a record, you can also partition horizontally into columns, into groups of columns. So I think the best way is actually in the documentation, this visual example here. A shard is basically the grouping of features that we're going to learn. It's what is our feature vector. And we've got another little level of granularity in between individual features and the shard, and that is feature sets. So oftentimes, why would you not want to learn some of the features? Well, if we're having a random effect per user model, we don't want the models to learn the user features. I mean, they're going to be, it's a waste of time. They're all going to be the same for each record because it's trying to learn its own features. So what we can do, based on that, the features we don't want to learn are all going to be grouped together in some way. In this case, it's a feature set. So we group together all the ads features into an ad feature set, all the job features into a job feature set, etc. And then you can use a shard to say, which feature sets am I going to learn? So what we're saying here is the shard, the features, the xij that we're trying to learn, is defined by global shard. Well, where is global shard defined? Up here in the shard to feature sets map, that's what this does. This defines global shard as the list of feature sets only named features in this case. And if we go back up to the data, we see here that that's our only feature set, features. And we also, this feature sets path, that is where we have our feature sets defined. There's files in there named after the feature set, and they describe what are the features in it. So update sequence and number iterations, I will come back to these in the next one. They'll make more sense there. So now we got this guy out of the way. What is the fixed effect opt stands for optimization, optimization configurations. Well, that's what the optimization problem that we're going to be solving, the convex optimization problem, is going to look like. So we have our global that we defined here. So global is going to have these parameters defining its optimization problem. So we have the optimizer type. Photon has two types of optimizers. We have Tron and LBFGS. Convergence tolerance. When we first start optimization, before we run the first iteration, we're going to have some zeroed coefficient values. We're going to have some dummy coefficients, and they're going to result in a starting objective value. And what we want to do is each time we run an iteration during the optimization problem, the convex optimization problem, we're going to improve the objective value. Now, this signals at one point do we stop. As long as the improvement in the objective value is greater than the starting objective value multiplied by this number, in this case 1 over 10 to the 5, as long as it's greater than whatever that number is, keep iterating up to the max number of iterations. So we might be finding that it's getting slow. We're not really seeing an improvement in our evaluation metrics. Let's cut it off early after 10 iterations. And then, of course, regularization. I heard some questions about regularization. So Photon does support L1, L2, and elastic net regularization. Tron, though, only supports L2 or no regularization. But if we want to, we could do something else. So let's just change that. LBFGS, I don't know, L1. Somebody who doesn't have a tutorial, shout out a number of iterations. What do we want? 6. I heard 6. Sorry, 1. 1 isn't a good number. Regularization weight, what's our weight? Somebody shout it out. Don't be shy. Okay, 1. There, 1's a good one for this one. All right, so now we can run that, and let's take a little look at what we get. So this stuff is pretty self-explanatory. It's not the main part of this tutorial. You can read through it on your own, the output logs, or you can play around with game later on your own, because it's open source, of course. So I'll just do a quick summary here. This section is data preparation, the times it took it. We're starting training. What is the model, or the combination of, what is our model? What is the combination of fixed and random effect models and other potential models that we're training? Here's the actual training information. So what's the metric after running an iteration? How many iterations did we run? Which coordinates did we descend? Then here, iteration 0 is over. We only had 1 up here, maximum iterations, so it's done after that. Here's the model that just finished training. You know, tell them what you're going to tell them, and then tell them what you told them. So lots of repetition. And then here is, so what you could have is game can train multiple combinations of models. For example, you might have a bunch of different random effects and more than one mixed effect. And you want to try them crazy combinations and see what's the best. Different regularization weights, different optimizers. This will pick out the best model by the evaluation metric and present it. So this is, and give you some info about it. So this is what this is doing. It's saying this is what the configurations for the best model, total model was, and here's our evaluation result. Here's some info. So evaluation result, we're doing logistic regression. So in this case, this is area under curve. So 0.77, there we go. If you play around with it, feel free to. This one's not a particularly interesting example, but you can play around with these settings again, run it, see how well it does. The hard data set is an incredibly tiny data set. I mean, 14 features, and it doesn't have very many records either. I'm not sure to the exact number. Please do not ask. All right, so what's the output look like? So here's our Avro record of the output, and this is our B. This is our B that we were training up here, our features vector for the global model. And here's what the output looks like. So the means is the values of the vector, and that makes sense. You know, we're trying to find the maximum likelihood. So these are the values that result, the values of the coefficients that result in the maximum likelihood for our model that we're training. See here, variances is null. Currently for the tutorial, it is disabled, but we also can compute the variances for each of these. And we see here that we've got our features. Now you see that we're missing some, right? We had 14, there's about 8 here. That means that they're below a certain threshold. I believe it's 1 over 10 to the 8 or 12. It's practically 0. They have negligible impact. Just 0 them. That's why, in case anyone was wondering. So there we go. That's our warm-up. That's a very basic model. You feel free to play around on it on your end. This one's not the more interesting part yet, so feel free to hold up as well. All right, so that's our section that we just covered. Are there any questions? No, everyone wants to keep going? All right. Oh, good.
So after you have those variables selected, will you output how that important it is, or like basically random forest generate some explanation for those variable, or it's just a random basically importance I see that 0 is it's not important.
Right. So this is the weights that lead to the best results. This is the weights of the coefficient of each feature.
So does that mean if the weight is 0, like if I only limit it to a few features, I will can cut it. I don't include that feature. So I basically don't include that feature.
Right. There is a limit. Like I said, it's around, I believe it was 1 over 10 to the 8 or 1 over 10 to the 12. If it's very small, if it's near 0, they get cut automatically for negligible impact. I believe that's what you're asking.
So I'm asking is if I have 1,000 features, if some output is 0, does that mean I don't need to include that feature? So for later,
Right.
optimization, I just directly remove that part.
Oh, if you'd like, you can do that. I mean, for this instance, that's what it says. You may want to keep them around. You may notice features later. All right. So next section what we got here is a mixed effect model. So now we're actually going to move on to that movie lens data set. And let's take a look at it. You can find more info here at this link up here. But let's take a look at it together. All right, so first off, each one of these records corresponds to a rating from a user to a movie. So which movie? Movie ID 1215, which user? User 1. This is the rating. And then this time we've got more than one feature set. So we've got genre features. These come from the movie lens data set. This is the genre information about the films. And then, oh, it's not those. The rating is down here. Here it is, the response. So it's a 4. This one has a 4. User 1 gave movie 1215 a 4. Might be pretty good. I'll check out movie 1215. All right. Sorry, as I was saying. Scale of 5. Scale of 5. Not 4 out of 10. So we have the genre features. These come from the movie lens dataset. This is the genre information. And then we have these movie latent factor features. These are some latent features that we computed through matrix factorization. We've pre-computed them, and we've added them in. I believe that's all the fields. Click that. Yeah, just one thing. If you click on the side here, this you can shift between all data and a little scroll window. Also, if you double click, you can minimize the whole thing and open it later for those people following along. All right, so what we're getting into now is, before we did like a GLM, just a standard problem. Now we're getting more into GL mix, as Shanxing was talking about. So we've got our fixed effect model here, but we've also got our random effect model per user. So we're going to set up one with a per user part to it now. So these are all the same, except for these random effect data configs. So just like the fixed effect data configurations set up what is our global problem that we're trying to solve, the random effect data configurations are setting up what is our per user random effect problem that we're trying to solve. So now partitions, shroud ID, these are familiar. This time we've got this random effect ID and it's on user ID. So what is this specifying? This is specifying what is our I. What is our I that we're training a model for each one? So this means that user ID, we go back up to our data, what we're going to be doing is we're going to be grouping all of our, for the random effect model, we're going to be grouping all of the records with the same user ID and forming them into a data set and working individually on that data set for each user. So this is saying group all the records for user 1 and then train that, just those records. That is our problem for user 1. That is user 1's coefficient vector. It's special to them. Then optimization configurations are the same thing as before. They're just like these ones. Now, this is a good time to explain. So we're doing a coordinate descent, right? So how do we know which order to descend the coordinates? Well, that's what this update sequence is for here. You see? So now that we've got this global, that's our global model, that's our xij that we're trying to learn. And then we've got this per user. So as before, that's this guy that we're trying to learn. Which order do we update them? Well, first we update global, then we update per user. That's the order we've defined here. Could easily switch them around as such. And the num iterations, that's the number of times we want to descend each coordinate. So if this were, say, 2, then we'd update per user. We'd fix the results from that, and we'd optimize global. Then again, we'd fix the results from that, optimize per user, and again, optimize global. So 2 run-throughs of the whole update sequence. So let's just bump it up from 1. 1's not interesting. Shout it out. Number, please. 13. 13 might be a while, so I'm going to cut that to 3. All right, and let chaos rule. If you want to change any of this stuff, shout it out. I'll change it. Otherwise, we can just run with this. I'll let you play around with it in a moment. No? No one wants anything changed? You want to see the good results? You want to move on to the recommender system? All right, let's do it. Let's lightning this. So again, it's running. It's a bit slower this time. It needs more data to prepare. While it's running, this might be an opportunity. So we assume setup will go smoother, and while you guys are all setting up on your own with no difficulties whatsoever, I had jokes prepared for me. I have not read these, so I'm going to read them now while we're waiting for this to run. It's not done yet. A physicist, a biologist, and a statistician go deer hunting. The physicist fires his gun and misses 5 feet to the left. The biologist fires and misses 5 feet to the right. The statistician says, "We got him." Is there only one joke on here? Okay, well, that was all the jokes. Thank you, Josh. He's right there, please. Round of applause.
The part when which are the user features, which are the per user features, and which are the global features?
So in this case, the global features. Unfortunately, in this case, we don't have user features. We've just got these kind of global features. They're both movie related, really. There's the genre and the movie latent features. So if we did have another feature set of user features, what we could do is it would look more like this. So note we're using just a global shard for everything in here. What we would do is if we had user features, the way we'd want to do this is we'd want to have we'd want to also have a or let's call it something, a user shard. And the way we do that is then we'd map this like such. So this one would still have the genre features. It should still have the movie latent factor features. But then this one would also, the global shard, this one would have user features. And as you see, they would be not included in the user shard because we wouldn't want to learn them. Sorry, and so up here, they should not be included in the user shard because if they were included, that would mean that the user, per user, each user would, in addition to trying to learn how the movie features affect it, would also be trying to learn how its own features affect its preference. But it would just slow down the computation. It would learn nothing because they'd be consistent for each user. So that's the idea behind having the feature sets in the shard. Oh, it's finally done. Usually it's not that slow. It might have been the additional iterations. So you see now we've got this, this start point. It's saying that the combination is of global and per user. And this time here, see that first it's updating the coordinate.
Consistent part on the user. The user's preferences might change, and what do you mean by it will be consistent?
So for each record, when a user is rating a movie, each one of those records is a rating from a user to a movie. So the user features would be info about the user. For example, their age, their location, their, I don't know, the profile name, maybe the things that they picked. For example, the Netflix example, you kind of say what genres you like in the beginning. So that's not going to change. If I rate, I don't know, Waterworld, those user features will be my user features. But then right after that, I go and I rate, let's say, I don't know, Scary Movie with a different rating. That record that's generated for that rating event, it still has the same user features. And they're not gonna add any information, because the whole point when we're learning is we're trying to see how different features about the movie affect the user's preference for them. But if we also add in the user's features to that, they're gonna be constant for each record specific to that user. So there can be a lot of features. So now, let's say we had 100 user features and 100 movie features. Now we're learning a problem that has twice as many features, where half the features, they don't matter, they don't do anything. We're getting no info out of them. Yeah, no problem. All right. So again, this time, see, it's running more iterations. Or first it did per user, then it did global, iteration 0 over. Now, again, per user, global, iteration 1. It's kind of like an array index. You add 1, so 0 is the first iteration. And then for the third iteration, there you go. Now, again, here's our result. So now we're doing linear regression. So our evaluation metric, it's not area under curve. It's going to be root mean squared error. All right. So, and then let's take a look at the output just again. So here's our global model again. Here's the features. They don't have cool names like last time because they're latent features. So they have amazing descriptive names like 2 and 11. You have executives going, really got to bump up the 11 on our films. Going down, and see here, oh, and then here, there are some for the genres, though. Children, this poorly affects the rating of movies, apparently. Same with war. Going through. So here we got fixed effect. That's our model ID. What this means is this applies to all users. This is the fixed effect model. And you'll see how that changes for this one. So here for user 1, I believe this is for user 1.
Can you give a little bit of explanation of those latent features? Like what
So is everyone familiar with matrix factorization and the way it can be used to get latent features? So yeah, we'll have time for questions afterwards. It's from matrix factorization. All right, so this is for user 41996. This is what the model ID means when you have a random effect. This is who is this? For which I should we apply this? I, in this case, is 41996. That's the user, and this is their movie preferences and codes. So you see this one, before we saw war was bad. This one, they like a little bit of war. They like a little bit of war in their movies. It keeps it interesting. So what we see here is after this, we've got this fixed effect model and this random effect model here for each user. Basically, what we've got is our recommender system from before. We're just missing a few of the bells and whistles around it. So let's add those in and see how this workflow might work in this kind of a toy example here of the movies. Before we move on, are there any questions about what we just saw? Right there. Sorry, she had her hand first. Yes. These are the coefficients for the, let me minimize that. Whoa. These are the coefficients for that user, the user in model ID. So that's the user ID of the user for which we computed that. So if we go back up to our equation here, for I equals that model ID, that was the A. No, the logistic we did earlier was kind of like a toy example. The global modeling mean it's all linear regression. We can't use the same features for both in this case. What you're talking about, the global model is the first one, I think. So the one that had the fixed effect in the model ID, that's the one that was the global model. That was the B. That results was the, what was that? Oh, because you can play with the text. Yeah. That was the B that we took a look at So, and then the second file that I opened, that was the AI, and for the I equals whatever model ID was. Sorry, you got a question?
Yeah, just to clarify my understanding. So the first model is across all movies, across all users.
Yes. Right. So the way to think about this is this first one, that's the preference, that's the global trends of all users towards all movies. That's in general, people, like the public, they think this of these movies. The second term is the preference of individual users to all movies. So for example, user AI, where I equals whatever, let's say 1, I'm number 1. User A1, they like movies that have more war. So this is what, kind of learning the deviation for each individual from the global mean. If we had another term here, for example, that would be the XJ, that would be the preference of all movies, sorry, the preference of individual movies towards all users. So, you know, like the Battlefield movie, or sorry, not Battlefield, Battleship. The Battleship movie, it might, like, the people who are going to rate it highly are people who are in this certain age group with this level of education, this level of income, and from this location. That's kind of the way to think about it. And then you can add in another term. For example, if we had a fourth term, it could be a matrix factorization term. And then that would be a loose estimate of the preference of a specific user to a specific movie. And then you could combine all of that to hopefully shrink and shrink and shrink this deviation from the global mean that we started out with. Were there any more questions? Right there. Sorry.
Question. So how do you choose the your result? How do you choose the order of the results? Previously, I see your relation name 97 to 11.
Mm-hmm.
It looks like you didn't update your results. So how do you choose the order? Why you first show the results in 27?
I don't quite understand the question. Where is it? So it should.
For the fixed fixed models,
Mm-hmm.
the coefficients.
Do you want me to go to data results, or do you want me to just go here? Result? Okay. This one is for the global model. Is this one the one you want?
Yeah. So why the first one choose the why?
Oh, the order doesn't particularly matter. This isn't an ordering in by value. This is just because it's stored in a hash, so it's unordered. Yeah, there is no meaning to the order of this. Sorry, you had a question, sir? We trained them for all the users. We just only printed one, because otherwise it'd just be a flood of input for every user we have in there. Yes, but of course, now you've multiplied your problem by 1,000,000 plus 1.
So in this case, we'll have two sets of coefficients for each variable because we are using the same global chart for both user features and
We'd have two sets of coefficients anyway. In this case, we just happen to be using the same shard for everything because we didn't prepare user features for this. If we had user features, like I demonstrated earlier, the shards would be different because the users wouldn't want to, for the user shard, we wouldn't want to include these user features in there. So see here we just have the movie features. We're just learning the movie features for the user, but the global model should learn all available features to capture as much input about the global mean as possible. Yes, sir.
So is it pretty common for real-world applications that use recommendations to have linear models, or are we just using that as an example?
I cannot speak to that. I'm more on the tech side. Shanxing? We had a question. So how often do real-world applications use just linear models like this, like GLM? Is this just a toy example, or more frequently would matrix factorization?
Open, right? So one reason is like industry. So there's a big difference between the models that's popular in academia and model popular in industry, right? In industry, you want the model. One thing we focus on is like simplicity. Like once you deploy your model in real production, you need to not only you want like the data scientists to understand the model, you also want like the engineers with like very limited like knowledge in data mining to understand the model. For example, if you launch a model to LinkedIn product, and one day LinkedIn is done, and the engineer they need to look at the problem. If like you run like deep learning model in production, it will be very challenging for the engineer to figure out the reason why the system is done. If it's a linear model, the engineer just can directly look at the coefficients and say, okay, maybe this doesn't make sense or something's wrong. They can easily figure out the problem. But it doesn't say we only use a linear model. For example, so one if we talk about a research paper, if you look at one of the recent paper from Facebook, discuss how they run their ads prediction. So what they do is the running model is still a linear model, it's still a logic regression model, but they use the more sophisticated model like the tree model, the GBDT, to learn those transformed features using the tree. They use those model like a feature transformer instead of the underlying response prediction model, right? In order to capture more complex feature interactions. And if you look at Google, if you look at most of their models they use for their ads prediction, like the Siebel, their machine learning system, it's purely linear model. And they spend a lot of time just working on to, for example, use deep learning to get embedded latent features to get some embedding of the features. But at the end of the day, it's still running a linear model.
What he said. Thank you very much, Cheng. Thank you. All right, so we're running short on time, so let's quickly try to move on to the app. This is the part where you guys will hopefully play around with the most on your end. So if you move on, you see here that we've got these 6 parts to it. Feel free to read the text for now. I'm going to summarize it for you. So the first thing is you're going to want to open this ratings app. Open this ratings app here. So some of you saw while Cheng was answering, I cleared my results, and let's try and go through this and just do an example of some ratings. So one thing that's helpful is you can do random. Random will just get whatever, in this case 100 random movies, and you can give them ratings. So let's see what kind of results we can get by rating some films. Now, people who have the tutorial working, feel free to play around on your own. I'm going to work with the people who had some difficulties. So here you go, guys. I'm going to be your agent. So I'm going to scroll slowly, shout out a name, shout out a rating. Let's see what we get. Space Odyssey. What are we rating it?
5.
5. We love it. Gold. Next. Someone just shout stop, please.
Billy Madison.
Where? Did you see it? Billy Madison. What do we think?
5.
Also, we have awesome taste. Citizen Kane 4. It is not the greatest film of all time. That is held by Billy Madison. 5. Okay. Are there any here? Let's just shout one. Maybe one you've never heard of, and let's give it a 1. Fargo, I heard 2. I'm sorry. This does not reflect my actual opinions. And what's that?
Do you have this group recommendation?
Oh, True Lies. There we go. I like this one, but 1. So there you go. Let's see what we get with that. So what we're gonna do now is we've done our ratings. Our strange user, possibly being controlled by Twitch, has done the ratings. The next thing we're going to want to do is we're going to want to import our ratings. So what we're doing here is actually doing 2 things. We're importing the ratings from our app, and we're also joining in those genre and latent features that we saw before. We're joining them in on the ratings data. So now we have a much smaller data set, but it's all for one user, and it's got that genre and latent features data in. Let's take a look at an example of what that might look like. Whoop, this one. So movie ID 216, if we go back, 216, that's Billy Madison. And we see the features that we joined in, the ones for. Let's go down, 5. That's correct, we did give it a 5. So now let's move on. What we're gonna wanna do is, so you know how in cooking shows when they all right, we've basted the turkey and we've stuffed it and all that, let's put it in the oven for 4 hours, but luckily I've got a cooked one right here. Well, this is what we got. We pre-trained our model on the whole movie lens. We've been working with a subset on the tutorial. We've got the pre-trained fixed effect model from the whole movie lens data set for you guys. We're going to score our rated data with that model. And now that we've scored it, what we're going to do is we're going to add those scores to the offset. So it's kind of like a partial score. During training now, what we can do is we will use those partial scores in the offsets to, well, offset the scores as they're being computed. So what we can do now is we can train this per user model. It's just a subset of the command we saw earlier. We can train it on just the data, making it much, much faster. So now we don't have to retrain that fixed effect model each time. We can do it piecemeal, which saves a lot of time and makes experimentation much, much faster. Plus, we've got a very small data set this time. It's only, what, like 6, 7 ratings from one user. So there we go, it's done already. So what we've got now is, somebody asked before, did we generate output for all the users? I believe it was user. All of them, or just one? In this case, we did generate it for just one. So now what we're going to do is we're going to generate a candidate set. The Movie Lens data set, as I mentioned before, it's pretty big. There's a lot of films on it, and even with those 500 that we had there, people didn't know some of them. People didn't know a lot of them. I didn't know a lot of them. We're all in this together. So what we got is a candidate set of 500 films from IMDb, the top 500 rated films off IMDb. So we're kind of getting this mix of movie websites. And what we're going to do is now we're going to score those films using a combination of that fixed effect model we pre-trained, and also now this specific per user model for this user that we are pretending to be together. So now we have those scores. What we're going to do is we're going to deploy them back out to the ratings app. I believe I just overwrote that. For those playing around later or playing around right now, what you can do is if you change this to a different name here, it's in the output path. You want to keep the 0.tsv, but you can change the directory between recommendations and the final output. That'll give it a different name. So let's call it testing123 and run it. And the reason I bring this up is because you can have multiple random effect models that way and check them at the same time, kind of compare between them. So now we've got this testing123 here in our models. Let's take a look at what we've got rated for us. So the first piece of advice is Ghost in the Shell. Didn't expect that. The next one is Star Wars. We've got 12 Monkeys, Shawshank Redemption, The City of Lost Children. I think I've seen something like this before. If you give it a very odd mix, if you don't have a theme going, if you're just kind of throwing out random numbers for ratings, or random films with 5s, as people, there's 2 and 3 and 4, but we all know people rate things 1 or 5. So if there's no pattern to capture, sometimes you can't capture a pattern. Yeah, it's captured it a little bit in the genres, maybe not so much the content. It's definitely got the sci-fi going, though. You're right about that. And here again, you can see Shawshank Redemption. The movies that we selected are kind of similar enough, and this is so highly acclaimed that it's coming through anyway. So what you can do now is you can play around with the ratings. It's a little bit difficult because it does keep the ratings that you had before. Should have had a clear button now that I think about it. But if you keep playing around with it, you can kind of rate more movies, rate less movies, rate different movies with a theme. You can find that oftentimes it actually does pretty good recommendations. So given that it's using, a candidate set, just a subset. So we are running a bit of time, and I would like to leave questions. So what I'm going to do is I'm just going to skip the question block for here, and we'll move it to the end. What we're going to do is we're going to move on to the last set. So we've got this final data set for you guys, and it's called the Search Ads data set. It's a synthetic data set created in structure similar to the KDD Cup 2012 Task 2 data set, which you can find more info about at this link. And you can run it and take a look at it. It's kind of big, so it's been summarized in this table here. This one has a lot of different feature sets, and it has a lot of different potential for squeezing out all that, all that information we're not quite getting with a global model. So this one is the much more general version of game. Once again, I'm just going to remind you that while these are all generalized linear models in this tutorial, game does handle matrix factorization, and as seen before, we are looking at deep learning as well. So don't think it's limited in a way that it's not. It's just a tutorial that's limited because it's supposed to be quick. So this one is kind of an experiment for you guys. So seeing what the data looks like and seeing the previous examples, for anyone who's interested, try configuring, I played around with that. Try configuring your own problem using as many effects as you can. Because what we're trying to create with this is we're trying to get a model it's got this hierarchy of granularity. And for those familiar with the idea of the God of the gaps, it's kind of like that. Each time you kind of shrink the gap and you give, in this case, instead of God, we have uncertainty. You give it less place to hide because each time we're adding that little bit more info. So, we might have a keyword and an ad ID and a query ID and a user. And what is the chance that the user is going to click this ad? Well, first we have our global model. We know, well, users in general think this about ads, but then, well, this user is more prone to clicking on ads. And this user also, they love shoes, and they just, in fact, searched for shoes. That was their query into Google. And then, what else is there? Maybe it's a certain time of day, and they're more eager. They're more likely. People are more likely to shop during that time of day. So you can just capture all this extra information you would regularly lose. You wouldn't lose, but you just wouldn't think to hold is a better way of phrasing it. So this is an experiment for people who are interested. There's no point writing it out. You should have it on your versions. What you can do is you can try run it. Now, one last note is that the results from this are kind of meaningless. This is a synthetic data set. This is for your own benefit to see how simple it might be to configure a very large model. How simple and quick it might be to configure a model that might take much, much longer to run because of all the data it's trying to squeeze out. And really, I believe that's the end of the formal part of the tutorial. So we're at 11:42 now. If anyone would like to play around and they'd like some help or advice or questions, we're going to stick around till 12 and answer. But I believe that's it for now. So thanks for joining us, everyone.